Hello everybody, this is Mrs. Handy here bringing you lesson 3 of our second unit in pre-calculus, solving equations with trig identities. Before we start actually looking at how to solve some of these equations, let's actually look at how we can check our work and know that if our answer is actually a solution. So that's what example 1's saying, right? Is x equals pi over 4 a solution to this equation? And you're going to have to kind of imagine that those square roots have a bar over them. I don't know why the computer isn't having that show up right now. So here we go with our first step. We are going to take our x equals pi over 4 and look at our equation, and anywhere there's an x, we plug it in. So nothing crazy happening here. We did some of this when we were graphing our trig equations. When we plug in pi over 4 then, I want you to look at the trig functions as being attached to those values, right? So we're talking really about tangent of pi over 4 and cosine of pi over 4, and then again tangent of pi over 4. And just use your knowledge of the unit circle to evaluate those expressions. So I'm just going to bring down the root 2. Then we know tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. And again, tangent of pi over 4 is 1. So I plug those in. The next step is to simplify. So when I take the square root of 2 times 1 times the square root of 2 over 2, that all simplifies to 1, right? So I've got root 2 times 1 times root 2 over 2. And if I think about all of these as having denominators, multiplying square root of 2 times 1 times square root of 2 just gives me 2 in the numerator. And then 1 times 2 gives me 2 in the denominator. And that simplifies to 1, which gives me this first term. And then obviously this one at the end, there's nothing to do with it but bring it down. And we know that 1 minus 1 equals 0. So since we have a true statement, 0 equals 0, we know that yes, pi over 4 is a solution to this equation. So what you just saw is the end result, right? We want to see if our solutions actually make the equation true once we get to them. Let's back the train up and talk about how we can actually find solutions in the first place. And you guys want to be prepared to be expected to do both of these things, either check solutions or solve for solutions when it comes to quizzes and tests. So notice we have the same equation we were just working with here, but the question now is just, are there more solutions to this equation? Find all solutions in the interval from 0 to 2 pi. So when we say that, we're just putting that on there so that you know we want answers in radians, and also we only want you looking at one positive revolution of the unit circle. And we don't need a calculator for this, right? So the first thing I want you to notice when you look at your equation is that there are two terms. This is one term right here, and this is our other term. Remember, terms are separated by addition and subtraction, and I'm only focusing on the left side of the equation right now. So when I look at those two terms, I can see that they both have a tangent in common. When terms have something in common, we can factor that common term out. So think greatest common factor. Think about if I divide this term by tangent, what's left? What would be left is the root 2 and the cosine, so that's what comes here. And if I divide this term by tangent, tangent divided by tangent is 1. Bring down the minus sign, and then of course the equals 0 on the other side. Now we can apply the zero product property that we learned in algebra. So when I have two things that multiply together to equal 0, one or both of them has to be 0 to make that equation true. So I can set tangent equal to 0, and I can set the square root of 2 cosine x minus 1 equal to 0. So both factors equal to 0. What happens next is kind of twofold. So let's kind of separate this out. We have tangent of x equal to 0. We already have the trig expression isolated here. In the other one, there's more going on. We need to get cosine by itself. So let's zip through that really quick. We know that we would add 1 to both sides, and then we would divide by square root of 2 on both sides. And then we would rationalize by multiplying by root 2 over 2 to get, root 2 over root 2 to get root 2 over 2. And that looks a little bit more familiar from our unit circle, right? So now let's talk about what's going on in this yellow space. We had problems in Unit 1 where we would just say something like, find all values of x that make this equation true from 0 to 2 pi. And you're just thinking about the unit circle and thinking about where tangent of x is equal to 0. What angles produce tangent of those angles that equal 0? So those answers for tangent are 0 and pi. Then I'm moving over to this equation and asking myself what angles could go in here so that when I take the cosine of those angles, I get root 2 over 2. Those two answers are pi over 4 and 7 pi over 4. So at this point in time, I'm really thinking about these as being my 4 answers or my 4 solutions to this equation. We've already checked and confirmed that pi over 4 is a solution. We did that when we first started with this example. But now we've found all possible solutions to the equation. So we're not quite done with example 1 yet. I want to talk about extraneous solutions. You know that we talked about extraneous solutions in Algebra 2. Many times extraneous solutions occur in rational functions. So when I'm talking about rational functions, I mean things that can look like fractions, right? Because tangent, cotangent, secant, and cosecant have variables in their denominator, we can kind of think of them like rational functions. They have the potential to be undefined. So if anytime we have 0 in a denominator, then that function is undefined. Similar again to rationals. So we've seen these answers of undefined when we evaluate our trig functions around the unit circle. So we want to make sure every time we solve one of these trig equations that we're asking ourselves, are any of these answers extraneous? We can check by making sure that when we plug values back into the original equation, we don't come up with anything that's undefined. So what we have here is our original equation, the equation that was listed on the assignment sheet. Then what we have here are the solutions that we came up with using the unit circle. So I've grouped them all together here. Yes, the 0 and pi came from the tangent component, and the pi over 4 and 7 pi over 4 came from the cosine component. But really, this list of 4 things, this is my solution set. So I'm going to check each of those values in the original equation and make sure things aren't, I'm not going to come up with anything that's undefined. So when I look at x equals 0, and I look at the ordered pair, when I take the tangent, I would take 0 over 1. Remember, 0 in the numerator is fine as long as we don't have 0 in the denominator. So I know that 0 does not produce an undefined answer. Similarly with pi, I would have tangent is 0 over negative 1. So that's going to be fine as well because it's 0. At pi over 4, tangent is 1 because we have root 2 over root 2. And then at 7 pi over 4, similar story, but I would get negative 1 from tangent. So tangent is not undefined for any of these 4 values. When I look at the other trig function, and I need to make sure I check every trig function in the original formula, cosine is never undefined, right? When we talk about cosine and its graph, it is continuous. It doesn't have any asymptotes. That would indicate that it has an undefined value. And its domain is all real numbers. So I don't ever need to worry about cosine or sine for that matter. And actually, that's a sine graph that I drew, not a cosine graph. But the point is the same. The domain is all real numbers. Cosine and sine are never undefined, so we don't need to worry about checking those against extraneous solutions. So in this case, no extraneous solutions. These are our 4 correct answers. So I hate to break it to you, but I'm still not quite ready to move on from example 1. I want to address a common mistake that some kids make when they approach these problems. So we're back to the same equation that we started with. Let's think about, again, our 2 terms separated by addition or subtraction, and that we can factor out the tangent because the tangent is common to both. A common mistake that people make is that they think they can divide both sides of the equation by tangent. And like I said, that's a mistake. It's a common mistake. So I want to address why we can't do that. Pause for a minute and let's look at this little thought bubble here. If we have the equation x squared equals x, the correct way to solve this is to subtract x from both sides. Okay, so we're getting 0 on one side, factor, and then use the zero product property to set each factor equal to 0. So we would get x equals 0, x minus 1 equals 0, we would get 1 as an additional solution. So there are 2 solutions to that equation, and you guys know that. If we plugged in 0, 0 squared is 0, and if we plugged in 1, 1 squared is 1. Those are both correct solutions to the equation. But there is an incorrect way to do this, which is kind of what I'm getting at. If we had x squared equals x and we divided by x on both sides, x squared divided by x would just give me x, and x divided by x would just give me 1. And so it looks like I just come up with one solution when I know there are 2 solutions to the equation. So when we divide by a variable, we have the potential to end up missing a solution at the end. Because tangent it's really tangent of x, and x is our variable, because that has a variable in it, we can't divide by it on both sides, because then we would eliminate the solutions that come from that component. Dividing by tangent on both sides would just leave us with root 2 cosine of x minus 1. I don't know why my thing isn't writing here. Okay, equals 0. We would solve that in order to get our pi over 4 and 7 pi over 4, but we would be missing the other 2 solutions that we know work, the 0 and the pi that came from the tangent component. So once you get 0 on one side, don't divide through by anything, because then you're going to miss some of your correct answers. So in general, here's how you can approach these problems. If you don't have 0 on one side, you want to get it there first. And we didn't see that in example 1, but we'll look at that in a minute. Then you want to factor, and remember what factoring means. So first thing you're going to do is look for a common factor, and we just saw that tangent was common to both terms in that last one. You won't always have a common factor though. Sometimes you're going to have to factor as if the expression were a quadratic, and we'll see that in a minute. And then later on, if we can't factor, what we might do is use the quadratic formula. So kind of stay tuned on that. It won't come up in this lesson, but it might later on in the course. After we've done some factoring, we're going to set each factor equal to 0 using the zero product property. We'll solve each new equation, and we will always check for extraneous solutions. And if we have extraneous solutions, we just cross them off and only list the remaining values as our solution set. So let's dig into example 2. New equation, same interval. So our answer needs to be in radians, and we're looking at 1 positive revolution of the unit circle. Starting with this equation, the first thing we need to do is get 0 on one side. So I added 1 to both sides. Done. The next thing we want to do is factor. Always check for a greatest common factor first. When we look at this, we want to ask ourselves, how many terms are there? And I'm hoping you see 3 terms here. So we have our sine squared is 1 term, 2 sine of x is 1 term, and then the 1 is 1 term. Because they don't all have something in common, there's no greatest common factor here. When there is not a greatest common factor, usually what you're going to find is that we can treat this like a quadratic. So I want you to look at the sine where the signs are here. And I want you to notice that one of them is squared, one of them is not. We can kind of think of our quadratics where we have a squared term, a linear term, and then the constant term. So come over here and let's suppose that we thought about sine of x as being some other variable, y. If we plug in y instead of sine of x here, we end up with y squared minus 2y plus 1 equals 0. And then we can factor that pretty easily. They both factors end up being y minus 1. So use this idea and come back over to our trig equation. Remember, we said that y was the same as sine. So now plug sine in to those y spaces, and we end up with sine of x minus 1 times sine of x minus 1 equals 0. Once we have our factors, when we have two things that multiply to 0, one or both has to be 0, so we set them equal to 0. Because these factors are the same, you don't need to do the same thing twice. So just set that one factor equal to 0. Solve, meaning like isolate the trig function, is our first step in solving. So get the trig function by itself, sine, by adding 1 to both sides. And then look at your unit circle and figure out what angle or angles make that true. In this case, pi over 2 is the only place where our sine value, our y value on the unit circle is 1. So that is our only potential solution. And then we just need to ask ourselves, is it extraneous? So the answer here is no, it is not extraneous. And we know that because when we take pi over 2 and we look back at the original setup of the problem, when we plug it in, nothing will be undefined. Sine, just like cosine, is always defined. It's continuous. It has a domain of all real numbers. So you don't need to worry about extraneous solutions when your original equation only has sines or cosines in it. So our final answer is that x equals pi over 2. And that's our only answer, and that's okay. On to example 3. Same story, new equation. Same first step. So we have cosine of x times tangent squared equals cosine. Go ahead, move the cosine over and get 0 on one side. The next thing you're looking for is common factors. So we have two terms here. They both have a cosine in common. So we'll factor the cosine out. After we've factored, we are looking at setting both terms equal to 0. Cosine of x equals to 0 already has the trig function isolated. Tangent squared x minus 1 equal to 0 does not. So we can add 1 to both sides, take the square root of both sides, and remember, whenever you take the square root, you need to have the positive and the negative square root. So we have plus or minus 1. Now, this problem from here actually could have been done slightly differently. So if we leave the cosine of x out in front there, and then because you're becoming more comfortable with our trig identities, specifically the Pythagorean identities, we've seen that we do a lot of factoring with the difference of squares. This tangent squared x minus 1 is the difference of squares. So we could, I'm not going to be able to fit it in there, we could have factored this into cosine of x and then tangent of x minus 1, tangent of x plus 1. So we could have continued to factor that, and then we would have those three things that we are setting equal to 0, but we would still get to the same spot where we have cosine equals 0 and then tangent equals both positive 1 and negative 1. So you can approach it either way. From here, we are getting these solutions with our unit circle. Thinking about where is it true that cosine of x or cosine of an angle equals 0, and where do we get results for tangent that produce 1 and negative 1. Once you have your potential solutions, check to see if they're extraneous. And here we're finally at a case where we do have some extraneous answers. So let's look at why. If I look at pi over 2 and 3 pi over 2 in my original equation, I know that plugging those values in for cosine isn't a problem. I get 0. I'm looking for, is something going to be undefined? When I plug pi over 2 in for tangent, and you can just ignore the square for a minute, just look at plugging it in for tangent. Pi over 2 is the ordered pair 0, 1. So tangent is 1 over 0. 1 over 0 is undefined. And undefined squared, I guess it's still undefined. So pi over 2 is a problem in our original equation. So that means it's an extraneous solution and I can't list it among my solution set. The same thing happens at 3 pi over 2. Negative 1 over 0 is undefined. So we also have 3 pi over 2 as being a problem. When I go to check the others, all of the pi over 4s produce root 2 over 2 or negatives, right? So cosine is always going to be either root 2 over 2 or negative root 2 over 2. Tangent is always going to be 1 or negative 1. And squaring 1 or negative 1 gives me positive 1. So none of these are part of the problem. It's only the pi over 2 and 3 pi over 2 that were extraneous. So my final answers are just the 4 that came from that tangent component. And the expectation in class is that we see all of this work. We see that you can identify these as extraneous and that you know these are your final answers. So I just have one more example for you, and I saved the best for last, the hardest for last. When we look at the equation that we have here, set equal to 0, well, that's done, right? We already have 0 on one side, so there wasn't really anything to do for that step. When we look at factoring, I notice that there are 1, 2, 3 terms. And yes, I have a squared term, a linear term, and a constant term. So I might be thinking that it's similar to that other one that we thought about as a quadratic. But the problem here is that the trig functions are different, right? We have sine squared here and cosine here. That doesn't mean we can't approach the problem. It's just what makes it a little bit of a harder problem. So we are going to look at the Pythagorean identities to save us here. We know the mother of all Pythagorean identities is sine squared plus cosine squared equals 1. If we rearrange that, if we solve for sine squared by subtracting cosine squared from both sides, we get this new relationship. Not really new relationship, just different version of the same relationship. And this is helpful because if we replace the sine squared with 1 minus cosine squared, that's going to get us to a place where we have all of the same trig function. We can make it look like a quadratic, and we can factor from there. So here we go. We have our sine squared. We're going to pop in 1 minus cosine squared in place of it. Then, when I'm looking at this whole mess on this side, I'm going to see if I can do any combining of terms. And I notice that I have 2 terms that don't have variables, so I can combine those. So now we're here. If I combine the 1 and the negative 3, I get negative 2. I still have a negative sign in front of my cosine squared. I still have my plus 3 cosine. That all stays the same. From here to here, I just combined the 1 and the negative 3. Now it's looking more like a quadratic that I could factor. I have my squared term, my squared term, my linear term, my constant term, and now they're all the same function. If you're like me, you don't like factoring when our squared term has a negative in front. So what I'm going to do is multiply everything through by a negative 1 in order to fix that. So now I have from negative cosine squared, I have the opposite, positive cosine squared. The plus 3 becomes a minus 3, the minus 2 becomes a plus 2, and then 0 is still 0. Like we did before, you're now going to think to yourself, okay, I'm going to think about this as just a much simpler quadratic. So if cosine x was y, I would have y squared minus 3y plus 2 equal to 0. And then think about how that factors so that you get the appropriate b and c values. Once you figure out the factorization, put cosine back in for y. So we have cosine of x minus 2 times the quantity cosine of x minus 1 equals 0. Zero product property. Set each term equal to 0 and solve. So cosine of x minus 2 equals 0, add 2 to both sides. Cosine of x minus 1 equals 0, add 1 to both sides. This problem is so long, I had to move up on my screen here to fit it in. So here's where we left off. Cosine of x equals 2, cosine of x equals 1. I now need to figure out what angles make that true on the unit circle. So I want you to think about cosine of x equals 2. There are no solutions that will produce such a result. And it's not just because 2 isn't a value on the unit circle. We have ways that we can solve equations that are not on the unit circle. That'll come up later this year, and you've done some of that in Algebra 2 as well. So it's not simply that it's not on the unit circle. It's more so that it's out of the range of cosine. So we know that when we graph cosine, just plain old cosine, no transformations to it, it's going to have a range of -1 to 1. So its amplitude, right, is 1. 2 is outside of that. So there isn't anywhere on our graph that our cosine curve hits 2, okay? The curve never gets that high. So that means this component, this cosine of x equals 2, doesn't have any solutions to it. You can try all you want. You're not going to plug anything in here that produces 2 as a result. It will always be a value between -1 and 1. So we know we don't have anything from this, and that's okay. It might come up from time to time. But we do also know that cosine of x can equal 1, and we know that that happens over here at 0. That's where our x coordinate is 1, and that's our only solution. Remember that we still need to check and see if it's extraneous. So when I look back at the original equation, so not this one that I used the Pythagorean identities for, but my original equation, and I plug in x equals 0, because the original equation only has sines and cosines in it, and both sine and cosine are always defined for all real numbers, we know that we're good. So it's not extraneous, and we can go ahead and list x equals 0 as our solution to this equation. I hope you found this video helpful. It should follow along exactly as your notes do, and just know that you can see me for residual questions.